Monday, so don't come here if you have class on Monday. All right, so we're going to talk about energy and matter today. We did all the density and unit conversion stuff. Hopefully that's going well with your homework. Chapter 3 homework is also up, so make sure to work on that. You may have noticed there was a practice quiz posted on Blackboard. That is to kind of get you ready for the first quiz, which will be next week. So we'll have our first quiz on Tuesday, right after the holiday, and that will be on the stuff so far. So what we did, unit conversions, and what we do today as well. The practice quiz should give you a good test as to how you're doing with that. If you've done all the homework from those chapters, it should look pretty familiar. Like I said, that's really the key to this class. Make sure you're doing all the homework multiple times if necessary, so that you have the practice to be able to do these things. It's not a good idea to take the practice quiz, which is like 6 questions or something, 7 questions, and just assume that if you know how to do those 6 or 7 questions, you'll be good for the quiz, because there's more material than that. So do all the homework, then take the quiz to test yourself and see how far you've come. But if you're doing the homework okay, you're getting the questions right, and you don't need to go back and look at stuff to answer the questions all the time, then you know you're where you want to be. So practice quizzes up there to help you out. All right, remember we'll have lots of quizzes ideally, so they won't individually be worth too much each. You'll be able to drop ones, especially like at the beginning when you're not sure how things are going, so hopefully that will help. All right, questions about that? The actual quiz will be in class, right? Not at home. So today we're going to talk about classifying matter and then energy and temperature and some things with that. Then lab on Tuesday will be kind of reinforcing some of those ideas so you can complete the pre-lab and stuff like that with what we do today. All right, so first, let's classify some matter. Matter can be classified in kind of 2 ways. One is by its state, like solid, liquid, gas. That's probably what we're most familiar with. We're going to get more into that at the end of the chapter when we talk about changes of state. But solid, liquid, gas. You've probably heard that before. Another way to classify matter that kind of gets into the chemical composition of matter is by composition. So another way to split up matter is to say that it's going to fit in one of 2 categories. It's either going to be a pure substance or it's going to be a mixture. Makes sense. We can separate those, or we can think about things that would fit into either of those categories. We're going to get a little bit more specific and talk about a couple different kinds of pure substances and a couple different types of mixtures. So there are 2 different ways that something could be a pure substance. It can be an element, or it can be a compound. An element is special because it only has one type of atom in its composition. The types of atoms are given on the periodic table. So this one's pretty easy to find. Anything that has the same name as something on the periodic table is most likely an element. So somebody give me an example. What's like a substance that's just made of one type of atom that's a pure element? Nickel, sure. So nickel is a metal. Right, you can buy a piece of nickel. I don't know where you would get that, but you could probably get that somewhere to do some stuff with. And nickel, it has the same name as nickel on the periodic table, element number 28. its chemical formula is Ni. So if you have a piece of nickel, that is made of all nickel atoms, so that's a pure substance and it's an element. What's another one?
Iron.
Iron, sure, another metal. Right, just made of one type of atom, iron. What about one that's not a solid? Oxygen, yeah. Oxygen gas. Also just made of oxygen atoms. Now it's O2. We'll get into that a little later in the semester why that is. There's 2 oxygen atoms per molecule, so the oxygen is always given as a chemical formula of O2, but it's still just made of oxygen atoms. So it's just oxygen that makes it an element. All right, so jumping over to the other side, compound. Compound is probably the trickiest one because it's still a pure substance, but it's made of more than one type of atom. So a compound is more than one type of atom. And those are going to be chemically bound together. But more than one type of atom that have a chemical bond between them, and we'll talk a little bit about what that means to have a chemical bond between them. So can you think of something that would fit into a compound? Like it's a pure substance, but it has more than one type of atom in it. Sodium chloride, sure. Water is another good one. Sodium chloride, like table salt. Water. What else? Another one? CO2, sure. Carbon dioxide. One of the things that we're going to be doing with these is being able to classify things where they go. So you'll see that on the practice quiz and on the real quiz, which category does a certain thing fit into. And probably the biggest mistake, the most common mistake, is people calling compounds mixtures because they have more than one type of atom. So it's tempting to think of carbon dioxide as a mixture of carbon and oxygen, but it's not. It's a pure substance. It contains carbon and oxygen that are bound together by chemical bonds. And in a minute, we'll talk about how we can determine that a little more, more clearly. So let's look over at the other side, the mixtures. And mixtures can also be split into 2 categories. I'm going to drop this down here so we have a little more room. Mixtures can be heterogeneous mixtures or homogeneous mixtures. Anybody know what that refers to? What do you think the difference might be between a heterogeneous and a homogeneous mixture? Yeah, that's a good way of thinking of it. Something that's all mixed together versus something that's not really mixed together. So homogeneous means, in this case, uniform composition throughout, meaning that all the way through the substance, it looks the same. It doesn't have areas of one thing and another thing put together. They're all there. So for example, salt water. That's a good example. What are the components in salt water that make up that mixture? What's one of them? Not a trick question. Water is one. So salt's the other one. Yeah, good. Yeah, so it's salt and water. So we might say sodium chloride plus H2O. All right. And that's a homogeneous mixture because, has everybody seen salt water before? You can probably imagine it, I guess, if you haven't seen it. You can't see the salt and the water as being separate in that mixture. It looks like one thing, just looks like water, because the salt is completely distributed throughout the water. So it's got a uniform composition throughout. You don't have salt on one side, water on the other side. Thinking about that, what's another example of a homogeneous mixture? Kool-Aid. Kool-Aid, sure. Cool. Is it ID or DE? Yeah, ID. Kool-Aid. What's in Kool-Aid? Water is one. Sugar. Coloring. Yep. And some sort of flavor molecules. Citric acid, probably, something like that. So yeah, a bunch of different molecules all mixed together, but it's all mixed together. You don't see those different things in the Kool-Aid. It just looks like Kool-Aid. Can anybody give me an example of a homogeneous mixture that is not a liquid? A cookie. Kind of depends on the cookie though, right?
Chocolate chip.
Chocolate chip cookie. So it all looks the same throughout. You don't see individual chips in different places in a chocolate chip cookie. All right, so let's change it to a sugar cookie, yeah, and that'll be good because we can actually put the other cookie in the other spot. So let's say sugar cookie, right? It's got all that stuff in it, all distributed throughout, but it looks all the same throughout the cookie. Yeah, and what about air? Air would be a homogeneous mixture. What's air made of? There's 4 main gases in air. We name them all. Oxygen's one, but carbon dioxide's another. What else is in air? What? Nitrogen. Not much hydrogen in air. There's a little bit of a bunch of different gases, but there's 4 main ones. We're still missing one. We got oxygen, nitrogen, carbon dioxide. Water. Water is the last one. Water vapor. Like humidity, kind of. Yeah, so air is a homogeneous mixture of a bunch of different gases. And again, it's all uniform composition throughout. You don't see the oxygen on one side, the nitrogen on the other side, and so on. So that leaves the last one, heterogeneous mixtures, where they are not uniform composition. And there's obvious separation. So let's go back to our example from before. A chocolate chip cookie. Where we can clearly see that there's chocolate chips and there's cookie. The other parts of the cookie we might say are homogeneous, but there's definitely different domains there. There's different compositional domains. What else would fit in this category? What? Water and oil, sure. You can see a separation there. You can see that there's definitely a water part and an oil part. Anything else you can think of?
Gas.
Yeah, gas and water, sure. Kind of like, you mean like gasoline?
Yeah.
Like in a car? Yeah, so that would be like water and oil. We think of gas as kind of like oil. Yeah. All right, so that's a lot of good examples. I mean, heterogeneous mixtures can be anything. It could be water with rocks in it, right? That's a heterogeneous mixture because you see the water, you see the rocks. They're not all together in the same thing. Okay, so we've got some examples, we've got some definitions. Let's think a little bit more about what makes these things different from each other, and how we can determine whether they're different from each other. So the one thing that really makes mixtures different from the pure substances, I mean, we talk about how they, aren't chemically bound. But one important thing is that mixtures can be separated physically while compounds can only be separated chemically. Mixtures can be separated physically while compounds can only be separated chemically. What does that mean? What's the difference between a physical change and a chemical change? Let's just take one of them. So what does it mean to separate something physically?
Remove something.
Yeah, to physically separate them. So in other words, a mixture is just things being put together really close together. And so to physically separate them, you just move them apart from each other, and then they're no longer together. The key thing there is nothing has changed about the components. When they made the mixture and when you separated the mixture, they're still the same things. So we could say physical changes preserve the identity of the components. When you make salt water, you take salt, you dissolve it in water. You haven't stopped having salt. You haven't turned the salt into something else. You haven't turned the water into something else. You just put those two things together. So when you separate them again, you still have salt and you still have water. So there hasn't been a change in what it is. That's the most important way to show a physical change or to define a physical change, that nothing changes about the identity of the components. So then a chemical change would be the opposite. Something does change. It does not preserve the identity of the components. It breaks them down or otherwise changes them. Think about water. So water is a compound. It can be broken down into hydrogen and oxygen if you pass an electric current through it. Hydrogen gas and oxygen gas are nothing like water. Right? They're totally different compounds. So by creating that change, we've turned water into something else, and that makes it a chemical change. Another example would be burning something. You've completely changed the chemical composition of whatever you're burning. You've turned it into carbon dioxide and water. It's not there anymore. It's something totally different. So what are some things, some physical, well, I don't want to use that term. What are some observational things that would show a chemical change? If you did something in the lab and you wanted to know if it was a chemical or physical change, what's something that might point you in that direction? Color, yeah. If you see like a dramatic color change, it's usually an indication that something has really changed its identity. If something goes from green to red, a chemical reaction has likely happened. There are some exceptions to that, but in general, that's a pretty good way to look at it. If there's a big color change, probably a chemical reaction. What else? What else could show a chemical reaction? Odor is another one, possibly, because some things just smell on their own. But if you like mix some stuff together and all of a sudden there was a new smell, that's probably a good indication that it was a chemical change. Somebody said size? What do you mean?
Like, I don't know, I was just thinking like baking a cookie and then breaking the oven.
Sure, okay. So I think in general, the reason I asked, in general, size is more of a physical change. Like if you have something big and you grind it down into little pieces, that would be a physical change.
Oh, yeah, that's right.
But yeah, but the chemical change, baking is a chemical change because of the gas form generally. So when you have your batter, you put it in the oven, and a few things happen. It gets bigger from the gas that's formed. It turns brown, so that's the color change from the browning reactions. It gets harder, things like that. So which is also chemical change. Yeah. And then the last one we sometimes look for, that we'll talk about in the second half of the chapter, is energy, is heat. If there's a change in heat, meaning it gets hot or it gets cold, that's good evidence that you're making or breaking chemical bonds. Because physical changes tend not to emit heat or absorb heat. Well, they can absorb heat, but they tend not to change temperature, I guess is what I'm saying, in an unexpected way. So one way to determine whether or not you have a pure substance or a mixture is to think about how you would separate it. Can it be physically separated, or does it have to undergo a chemical reaction to change into something else to get separated? So let's practice this. We can look at a couple of the problems in the book that are about this. These are the types of things that you'll see on the quizzes and exams. So you've got physical or chemical properties. Here's pull this one. What type of change, physical or chemical, takes place in each of the following? So A, pie dough is rolled into thin pieces for a crust. Is that a physical or chemical change? Most people say physical. Why physical? How do you know? Yeah, you're just changing the shape. You're not changing the identity of what those components are. You're just changing the shape. Good. All right, a silver pin tarnishes in the air. You know what tarnishing is? Yeah, that's chemical. So you've got the shiny silver pin and it's becoming dull and gray. That's evidence that something chemical is going on. A reaction is happening that's coating the surface with a new type of a chemical. A tree is cut into boards. Physical, yeah, right? You're just changing the size, you're not changing composition. Food is digested. Right, that's chemical. So you've got digestive enzymes and things breaking down. What? It's really both, yeah. Depending on how you define digestion. Right, because you like chew it up and then you churn it around and stuff like that. I think digestion here is talking about like specifically the chemicals, like the enzymes going at the food, and that would be chemical. And then finally, a chocolate bar melts. Yeah, that's physical. Changes of state are always physical. So melting, boiling, freezing, that kind of stuff. That's physical change. Again, you're not changing the composition. You're not changing what it is. You're just changing its state. So that's physical. Okay, good. You can do that. All right, let's try one where we classify components here. Oops. Oh, you know what? They didn't have that here. Anyway, they're in the back. We'll revisit that. So that's basic classification of matter. Oh, there it is. Okay, I just didn't see it. You want page 61. Classify each substance as a pure, or each of the following as a pure substance or a mixture. So soft drink, what do you think? Mixture, yeah. You got water, you've got carbon dioxide, you've got whatever. Would you call it a heterogeneous or a homogeneous mixture? Homogeneous? Kind of depends on the soft drink, right? If it's carbonated, I would say it's probably heterogeneous because you can see the bubbles, right? So that carbon dioxide is different from the rest of it. But if it's like a lemonade, then yeah, homogeneous. What about propane? Yeah, propane's a pure substance. How do you know? Yeah, you've got a formula there. So does that make it an element or a compound? A compound made of a few elements. Yeah. Skip one. A cheese sandwich. That's gonna be a mixture. Which type of mixture? Heterogeneous. Yeah, you can see the cheese. You can see the bread. An iron nail. Pure, and what type of pure substance? Yeah, that's an element, just iron. Finally, salt substitute, KCl, potassium chloride. What do you think about that one? Pure? Pure, yeah. And it's a compound, right? Two different elements together in a chemical compound. Good. All right, so I think you can do that. Let's look at temperature.
You said the salt substitute with a compound?
Yes. So, temperature. What is temperature? Anybody know? What does it measure? Yeah, how hot and how cold something is. And what causes that? It's actually measuring atomic or molecular motion, so how fast molecules are moving around. That's really what temperature is. It's not a measure of heat. Heat is a transfer of energy. Heat can raise or lower the temperature depending on which direction heat is traveling, but temperature doesn't directly measure heat. It measures molecular motion. So there are three important temperature scales. We'll use mostly two of them for this class. I want to show you this picture. I think it's helpful. If I can get it all on the screen here. All right, there's our three temperature scales. I like this figure. They're all laid out in a way that makes a lot of sense. There's the Kelvin scale, the Celsius scale, and the Fahrenheit scale. The Fahrenheit scale is what we're most used to, of course. The Celsius scale is what we'll use in lab. And the Kelvin scale, we won't use much in this class. You should know that it's there, but we won't use it much in this class. The special thing about the Kelvin scale, does anybody know what's special about it compared to the other scales? Yeah. It's not measured in degrees, right? So instead of being 100 degrees Kelvin, we say 100 kelvins. So a Kelvin is actually a unit, just like a meter or a gram. And you can have microkelvins and millikelvins and whatever, like everything else. You can't have that with the other scales. And the reason that works for kelvins is because the Kelvin scale stops at 0. There are no negative numbers in the Kelvin scale. So at 0 is when there's no molecular motion at all. That's the lowest possible temperature. That's called absolute 0, and that's 0 kelvins. So when you need to measure things that are really cold, the Kelvin scale is useful. And when you need to do calculations where the scale can't go below 0, the Kelvin scale is really useful. Because think about all our other units, grams, meters, whatever. We never go below 0, right? So if you're doing calculations where temperature needs to be in there, you need a unit that doesn't go below 0, and Kelvin works for that. All right, so let's focus on the ones that we're going to use more here, the Celsius and Fahrenheit scales. Zoom in on this a little bit so you can see it. In this example, these thermometers are in boiling water. So you see the red line is up to the boiling point of water, which is 100 degrees Celsius or 212 degrees Fahrenheit. Also labeled on this diagram is normal body temperature, 37 C, 98.6 F, and the freezing point of water, 0 degrees C, 32 degrees F. You need to know those 6 numbers. You should know boiling point of water, normal body temperature, and freezing point of water at both scales. We're going to talk about how to convert from one scale to the other, but if you know some of the basic, like common temperatures, that'd be a good way to tell if you're correct or not when you do the conversions. Converting from one scale to the other is a little tricky because it's not a simple conversion like we did last week, or Tuesday. It's not as simple as setting up a ratio and multiplying it by something. The reason for that is there's two things you need to correct when you go between the Celsius and Fahrenheit scales. One is the size of the degree. So you'll notice that between the freezing point and boiling point of water, there are 100 Celsius degrees, but there's 180 Fahrenheit degrees. So a Fahrenheit degree is smaller than a Celsius degree. So there's the first need is to convert that part. Then also, they're offset. So the freezing point of water in Celsius is 0. The freezing point of water in Fahrenheit is 32. So the Fahrenheit scale is offset by 32. So to convert between the scales, we need to change the offset, so change where the starting place is, and also change the size of the degree. So that makes it not something we can just plug in nicely to a conversion factor thing like we did before. They have their own equations that you need to use. And they look like this. To convert from Fahrenheit to Celsius, if you want the Celsius temperature, so we'll call that TC, the Celsius temperature, you take the Fahrenheit temperature and you subtract 32 to get back to 0, or whatever, to get back to the correct scale, and then you divide by 1.8. You don't have to memorize this formula. It'll be given to you on quizzes and exams if you need it. But the key to this formula is you have to remember to subtract 32 before you divide. And if you have a modern calculator, like a scientific calculator or a graphing calculator, and you just type in some number minus 32 divided by 1.8, it won't give you the right number because it'll do the division before the subtraction, because that's the correct order of operations. So you need to make sure you go something minus 32, enter, and then divide by 1.8, or use parentheses if you could do that. So the subtraction has to be first. The opposite one, if you could do the algebra and rearrange that, but I'll just do it for you here. If you want to instead solve for the Fahrenheit temperature, you take 1.8 and you multiply that by the Celsius temperature, and then subtract 32. That one doesn't tend to, or I'm sorry, then add 32. That one doesn't tend to cause problems so much because you do the multiplication before you add, and that's what the calculator wants to do too. So that's how you would convert between scales. The Kelvin temperature is simply the Celsius temperature offset by a certain number. So the Kelvin temperature is the Celsius temperature plus 273. So to get kelvins, all you need to do is add 273 to the Celsius temperature. And again, you don't need to memorize these equations. You can practice using them in the homework. Just plug the numbers in and go from there. And if you need to do those conversions on the exam, those formulas will be given to you. So now that we know some things about temperature, we can think about energy and how temperature helps us understand energy. What is energy? Something that you all have a lot of right now? Not so much. What is it? What? What's energy? Yeah, what does that mean? So it's defined in the book as the ability to do work, or the capacity to do work. It's a tricky definition. Energy, I think, is more easily defined in how it's transferred. So when you transfer energy to something, there's two ways that can happen. One way is called heat. So if I am warm and I touch something that is cold, heat will flow from me to the cold thing, right? You've experienced this before, something like that. So heat can flow from something with high energy to something with low energy. Energy is not created or destroyed. So when heat when something gets warm and something else gets colder, that is energy transferring from one thing to another. So that's one way to transfer energy. But let's talk about this work thing. So the capacity to do work is another way of transferring energy. So if I lift my bag up like this, I've transferred some energy from me to the bag. Because the bag is now at a higher energy state than it was before, because when I let go, it will drop and do other stuff. So yeah. So that's what it means, capacity to do work. It allows you to transfer your energy to do something, whether it's to make something warmer or give something else more energy by either lifting it up or pushing it or something like that. So energy isn't created or destroyed. We just transfer it. We push it around. The work thing is more in the realm of physics, so we're not going to really mess with work too much. What we're going to be more interested in is heat and the transfer of energy via heat. So let's look at the units of energy. Does anybody know any units that energy is measured in? Watts is power, so that's close. Joules is one. You know any other ones? Kilojoules is, yeah, like joules with the kilo prefix. So we can look at that one. The symbol for joules is capital J. Okay. Calories, yeah. Calories just abbreviated cal. We know any other ones? Those are the important ones. There's a couple, I'm not even going to write them down, but a couple that are used in like household energy things. So watt is a measure of power, but if you multiply power by time, you get energy. So our house meters are usually read in kilowatt hours, which is actually a measure of energy. There's another one called a British thermal unit, or BTU, that's a measure of energy. But in the lab, we'll generally use joules and calories. So let's look at joules and calories. Let's look at a relationship between them. So first of all, 1 calorie is 4.184 joules. You don't have to memorize that number. But we could use that to then convert between calories and joules depending on what unit we want. There's a strange thing that happens, I think, just in this country with calories, that when we report calories like for food, it's actually not the same as that kind of calorie. Does anybody know what the difference is between like the calories on a food label and these calories? Just one letter. Right now. Capital C, calories. Here. Let's do this. Calorie. 1 capital C calorie, which is the food label calorie, is actually 1,000 of the little c calories. Or more correctly called 1 kilocalorie. So most of the world measures their food calories in kcals. We use capital C calories. So we'll be doing some calculations, especially in lab on Tuesday, where we look at food calories, and they're listed on the label with a capital C. So make sure that you understand that that's 1,000 of the little c calories. Does anybody have a label, food, snack, or something? Yeah. Yeah. So I can show you this one. This is a granola bar. Try my book again. This thing will show up in a second. put this on the other side. Oh, that's terrible. Can't see that at all. Oh, what? All right. So you see there, it says calories 90, and that's capital C calories. So I'm going to write this down because we're going to do some calculations with that. We can calculate the amount of calories from the macronutrients. Does anybody know what macronutrients are? What are the 3 macronutrients that are in food? Yeah, fats, proteins, and carbohydrates. Good, thanks. So if we look at the total amount of fats, carb, and protein, you can see it there. 2 grams of fat, 19 grams of carbohydrates, and 1 gram of proteins. I know you can't see this, but I'm just writing that down right now. All right, thanks. So this is in our granola bar. We can figure out the calories based on those macronutrients because on average, the macronutrients have approximately the same energy density within their category. So fats are generally 9 kilocalories per gram. So that means every gram of fat contains about 9 kilocalories of energy. Carbohydrates and proteins have 4 kilocalories of energy per gram. So the same amount of energy. Now, that's from a purely chemical standpoint. That's the energy held within the bonds and those things. How it's used in your body can be a little bit different. So we're not saying that they're the exact same, but they have the same chemical energy in them. There is a big misconception, though, that everyone needs to eat way more protein. You heard this? That, like, it's good for you if you just always eat things that are really high in protein. It's not really true. If you're not using that protein like like you're an athlete or something and you're using that protein, it just turns into energy, just like anything else that you would eat. You just burn it off. So how do we do this? Well, we can take our quantities of fats, carbs, and proteins and convert them into energy, just like we did the other conversion problems. So we can say something like this. 2 grams of fat. And then we can set up a factor that gives us our calories from grams. So fat has 9 kcals per gram. So that tells us that those 2 grams of fat in that granola bar give us 18 kcals of energy. We can do the same thing with our carbohydrates. Whoops, not 19, 4. That's 4 is 76. And then our 1 gram of protein. Okay. So if you add those up, what do you get? $98. So that's pretty close to the label is 90. label's only using one significant figure. So if we rounded those, we would get 90. I mean, if we round 98, we get 100. But if we rounded all the other numbers in the interim, we'd get 90. So that's one way of looking at how much energy is in something. We can look at what's called the energy density. When we do this in lab, then make sure that the capital C calorie is actually the kcals that we're looking at. Okay. So we can practice that in a little bit too. All right, one thing we should know about that calorie unit. One calorie, little c calorie, is the amount of energy it takes to raise 1 gram of water 1 degree C. That's kind of where that unit comes from. So you have 1 gram of water, which we know is also 1 milliliter of water, since the density of water is 1. So if you have this much water at whatever it is in here, 23 degrees or something, if you wanted to raise it 1 degree, you have to put in 1 calorie of energy. That's how a calorie is defined, a little calorie. So if you had a liter of water, how many calories would it take to raise that liter of water 1 degree C? Yeah? Well, first let's figure it out. So how many milliliters is in a liter? 1,000, right? So how many grams is in a liter? Grams of water. I think there's sort of nothing. You can say it. It's 1,000 also, yeah. Because water is 1 gram per milliliter. So if you got 1,000 milliliters of water, you got 1,000 grams of water. So if each calorie raises a gram of water 1 degree C, how many calories do you need to raise 1,000 grams of water 1 degree C? Yeah, 1,000 calories, right? Yeah, 1,000 calories. So one of those capital C calories, 1 kcal, 1 food calorie, is the amount of energy that it takes to raise a whole liter of water 1 degree C. So if you took all the energy in that granola bar and used it to heat a liter of water, how hot would the water get? Do you remember how much that was? It was 90 kcals. So how many degrees could you raise water? Could you raise a liter of water with 90 kcals? Yeah, 90 degrees. Each kcal raises a liter of water 1 degree, so that would be 90 degrees. You couldn't actually do that because the water would start boiling and that takes more energy, but it gives you a sense of, so if you had that granola bar and you used all the energy in that granola bar to burn it, to absorb it into a liter of water, the liter of water would get up to the boiling point. All right, so what that means is that it takes a certain amount of energy to raise a certain amount of a substance, 1 degree C, and this is called specific heat. So specific heat is the amount of energy it takes to raise a gram of a substance 1 degree C. The specific heat of water is 1 calorie per gram degree C, which is a number and symbol way of writing what we just said, that it takes 1 calorie to raise 1 gram of water 1 degree C. And that's the specific heat of water. Other substances have other specific heats. So let's look at how that would compare with some other compounds. There's my table of specific heats. We'll just grab some. It's not the whole table. We can look at some of them. All right, here's some different specific heats. In both calories and joules. Doesn't matter that it's one or the other. So what you see here, let's look at the calories since we just said that water was 1. What's one thing you notice about all of these substances compared to water? They're all what? Yeah, they're all less than water, and water is pretty special in that regard. Water has an extremely high specific heat of 1. It means it takes a lot of energy to heat up water compared to other substances. So look at all those metals in that top part. Those all have really low specific heats. So you can think about that like this. Let's say you had a big block, a liter, or a big block that was a kilogram of metal, like aluminum or something. And then you had a bowl of water right next to it. You put them both out in the sun. Which one would get hot faster? The aluminum, right? Has anybody experienced that? You go outside on a hot day, stuff that's metal is really hot, right? You leave a water bottle in your car, it's not going to get nearly as hot as the seatbelt. You know, the like metal piece of the seatbelt, right? Yeah, people like go like that. Yeah. Yeah, it's terrible. So, and that's because of specific heat. You're getting the same amount of energy into that car, but the energy going into the metal is raising the temperature faster than the water because the metal has the lower specific heat. So specific heat we can think of as like how fast does something heat up when you heat it. For water, that's relatively slow compared to most other things. All right, so one way we can think about this, we'll come back to specific heat in a second. Let's look at changes of state of water and then think about how this comes into that. You know most of this already because you are a person who lives in the world, but we'll put it all in one place anyway. So what is it called when a solid becomes a liquid? Melting, right? Did you know that word? Okay, I hope so. Like I said, you're a person who lives in the world. You probably know some of these things. There are a few bits that you may not know, so we'll emphasize those. But I'm not going to spend all day talking about what melting is. So let's just grab this graphic from the book. This is page 76 if you're following along. All right, if we're going from ice to water, that's called melting. If we're going from water to ice, that's called freezing. From a molecular standpoint, you can see what's going on here. That when something melts, when something is a solid, it has a rigid molecular structure. When something is a liquid, the molecules are still very close together, in water's case actually even closer, but they can now move around more freely, which allows the liquid-like thing. And then when that water becomes water vapor, you have what's called vaporization or evaporation. And the opposite of that is condensation, gas becoming liquid. And in this case, all those water molecules are now separate from each other. So they're floating around individually. They no longer have an attraction. They're no longer close to each other. And that's the difference between a gas and liquid. Some words you may not know. If you go directly from a solid to a gas, that's called sublimation. And if you go directly from a gas to a solid, that's called deposition. Does water do this? Yeah. Can you go directly from ice to water vapor without melting first? They actually can. If you ever notice in your freezer, there's something called freezer burn. You know what I'm talking about? When your stuff kind of dries out and gets like gross. Yeah, that's what's happening. Because in the freezer, water can't melt. It's not warm enough for it to melt. But what it can do is it can become a vapor. And so it can leave your food. The water can leave your food and dry out the surface just because of sublimation. It's a much slower process, so it's not something we really see. But if you leave that stuff in the freezer a while, especially if it's not sealed, that water's going to be gone. It's going to be dry and gross. Ice cream gets all like crystally and gooey and stuff. Yeah. And the same thing with deposition. That happens in the freezer too. Again, it's too cold for the vapor to condense and then freeze. So what happens is the vapor itself actually freezes and it deposits and becomes ice. And that's how you get like those ice crystals or that frosty stuff around the outside of your freezer, that kind of thing. Some of that is coming from the atmosphere, but the stuff that's inside is from that deposition. So all these things are always happening in any sample of water, depending on the temperature, but some more than others. So that's the states of water, and that's how water changes state. We can track this by something called a heating curve, which is an interesting kind of graph that actually gives us a lot of information. Let me grab the heating curve for water here, and then we'll analyze through it together. So you'll notice if you're going through the book on your own and doing the homework, we're skipping a lot of the calculations in this chapter. That's on purpose, that's by design. So if you look at the homework numbers that are assigned, it skips all that stuff. So don't get bogged down in the heat calculations. That's not part of the class. All right, here's our heating curve for water. What this is a graph of is it's showing the temperature change based on the heat absorbed. So on the y-axis, you have the temperature, and on the x-axis across the bottom, you have how much heat are you putting in. Another way of thinking about this is like as you're heating something, what's happening to the temperature. So as we go from left to right on the graph, we're putting in heat to water. And then how high the graph is telling us how hot it's getting. So how much the temperature is changing. So let's track this through and then see what's happening and what's kind of unusual about it. We start way down here at the bottom. We're at minus 40 degrees C, which means we have ice. So as we add heat to minus 40 degree ice, the ice warms up. And it warms up and warms up and warms up as we add heat. And then all of a sudden we get to 0. And what happens? It melts. So why is the line horizontal here? What is that showing? What does it mean for the heating curve to not go up at all, but just to go horizontally? Yeah, so we're adding heat, but the temperature isn't changing. Where is the heat going if the temperature isn't changing? So the heat is going into the ice, but it's not changing its temperature. What is that energy doing? It is. Yeah, so the temperature is not changing. Temperature is staying the same, but the heat is going in. So what's the heat doing? By what? The what? Yeah. So the heat is changing the state. It's causing it to go from a liquid or from a solid to a liquid. It's melting the ice. So another way to say that is melting requires energy. So the energy has to go in there and melt the ice, break those water molecules apart. And that's why the temperature doesn't change. Because the energy that we're putting in is being used to break those water molecules apart, not to just raise the temperature of them. Let's go back and look at that picture of the state changes here. I guess it's here again. So here we had this rigid connected network. Now we have this loose water thing. It takes energy to do that. we have to put in energy to break those water molecules enough for them to become a liquid. So when you heat up ice and you get to 0, you actually have to put in more energy to get it to melt. So melting absorbs energy. Now we're at the liquid phase, and we just start heating it up again. So we're adding energy, we're heating this up. Remember, the specific heat for water says every degree we put in, every calorie we put in heats up a gram of water 1 degree. So we're heating it up linearly. And then we get to 100 degrees, we have the same thing. We have this plateau again. So what does that tell you? Yeah, the water requires energy to boil. Now, based on this graph, does it take more energy to boil water or to melt ice? How do you know? Yeah, it stays the same temperature for longer. So you have to put in way more heat to boil the water than you did to melt it. And this isn't quite to scale because it would actually be like really long. But we can put some numbers in here. The amount of energy it takes, let's see, let's do blue. The amount of energy it takes to boil water, make sure I got the right number here, is 540 calories per gram. So every gram of water takes 540 calories of energy to boil. For melting, it takes 80 calories per gram. So a lot less. How many calories does it take to heat liquid water from 0 to 100? So this curve here, if we say it starts about here and goes to about here, how many calories is that? For 1 gram of water, how many calories does it take to go from 0 to 100? A 100, yeah. Each calorie raises that gram of water 1 degree C. So if we want to go up 100 degrees, we need 100 calories. And that to me is kind of remarkable, that it takes 100 calories to heat up water from freezing point to boiling point, but it actually takes over 5 times that amount of energy to boil it. And you can see this like on the stove if you've ever boiled water. You ever boiled water? Nobody? Hopefully, maybe not. You put the water on the stove, you turn on the gas, it gets hot pretty fast, right? Like, it gets hot enough that you can't stick your finger in there relatively fast. But then it takes a while to boil, even after it's gotten hot. And that's because of that. It takes a lot more energy to break those water molecules apart from each other and turn them into a gas than it does to just heat them up.
Could you please tell me why you have 80 calories again, where?
Yeah, it takes
plateau there?
It takes 80 calories of energy to melt a gram of ice.
Okay. So it's 80. So from negative 40 to where we went to 0, that represents 1 gram?
It could, but it doesn't. I mean, it's any amount of water, but we're saying that each gram requires 80 calories just for the melting, not for the changing the temperature, just for the melting. But changing the temperature takes energy also, a different amount. Now we can, but we're not going to say how much energy it takes to heat up the gas and the solid, because those actually have different specific heats than liquid water. Let me see what's in here. Yeah, so solid water vapor, it's not given, but solid water, ice, is about half a calorie per gram degree C. So solid ice takes about half as much energy to heat up as water does. And that's just a function of how it is molecularly. We can see that on this diagram by the steepness of the line. If you compare how steep this line is to how steep this one, you see how this one's more like shallow? So that tells you that the heat that goes into liquid water doesn't raise its temperature quite as fast as it would with solid water. Solid water's temperature can raise more quickly with the same amount of energy. So it's more like a metal in that way. So that slope is a function of that specific heat. Let's try this. Let's see if we can read a different heating curve of a different substance and still get what we need for it. Now in lab on Tuesday, we're going to experimentally construct a heating curve where we actually heat it and measure the change in temperature and then graph it. So you'll get a chance to do that. Let's look at page 89. Let's look at one of the homework problems. So here is a heating curve for not water, but a different substance called chloroform. And let's answer some questions about chloroform. Goes on the next page, that's what I got to. All right, so first, based on that heating curve, what is the approximate melting point of chloroform? About what temperature does chloroform melt? Yeah, -60. So which, we can just go down to see which segment would represent melting. B, segment B, because we've got the solid initially at the coldest temperature. We heat up the solid, and then we melt the solid. So that's B, that's happening at about -60 degrees C. What's the approximate boiling point of chloroform? Yeah, about 60 degrees C, because we've got solid, melting, liquid, boiling, gas. So it's boiling right here, right about 60. All right, so I just said all those things for part C. Part D, at the following temperatures, is chloroform a solid, liquid, or gas? So what is the state at -80? It's a solid. You see that? Where would -80 be? Right here, between -60 and 100. So that's while it's still a solid as it's being heated up. What about -40? That's going to be a liquid. Yep, right here. 25 degrees C. Still liquid. And 80?
Gas.
Yeah, now it's a gas up here because 80 would be right there. So that's in the gas portion. All right, good. We got 5 more minutes. Let's try one more. We won't have to answer all these questions. But everybody grab some paper if you don't, or on your paper that you're using right now. Now we've got a different compound, dibromomethane. Melting point is -53 and the boiling point is 97. Sketch a heating curve from -100 degrees C to 120 degrees C. So see if you can draw a heating curve for this new substance given the melting point and the boiling point. All right, so you got your axes, something like this, temperature on the y-axis and heat on the x-axis. You're going to be adding heat and then looking to what's happening with the temperature. This is easiest to do if you first set up your landmarks, like the temperatures that you know you have to do stuff at. So the question tells us start at minus 100 and end at 120. Okay. Makes sense to kind of divide that relatively evenly. So if we go, let's see, halfway between minus 100 and 120 is about 0, just less than 0. So if we go 0, let's do it in 20s, 20, 40, 60, 80. Yeah, that didn't really work out, but that's all right. So minus 20, minus 40, minus 60, minus 80, something like that. So that means 97 is going to be just above 100, or sorry, just below 100, and minus 53 is just above minus 60. So that's going to be like about here, whoops, about here and about there. So then we can put in our curve. We're going to heat up the solid. Once we get to the melting point, we have a plateau. Then we go up to the boiling point again and there. How do we know how long to make those straight lines? Yeah. We don't is really the answer there. It doesn't give us that information. So you can make it as long as you want or as short as you want. Same thing with the steepness of the lines. We're not given any information about that. So really what this question is just saying is, can you put the shape in the right, can you make the shape right and have it doing its plateaus at the right spots? That's all the information we have. We can't really do any better than that. So that's why a lot of times on these heating curves, the x-axis, there's just no units because we don't have that information. We just know this is the general pattern, and that's all. All right, that's all the time we've got. So happy homeworking. Send me questions if you've got them over the weekend. And we will try out the practice quiz, and we'll do a quiz next week. Energy and Matter Lab on Tuesday.